In both of these diagrams, we have two lines cut by a third line called a transversal. Again, two lines cut by a third called a transversal. In the first picture, these lines are parallel, and in the second picture, these lines are not parallel. But we can still number the 8 angles that are formed the same way, and this description of the angles down here that we're going to talk about applies equally to this picture as it does to that picture. Alright, first, corresponding angles. Corresponding angles are in the same relative location. For example, 2 is in the upper right of this group of 4 angles, and 6 is in the upper right of that group of angles. So they are corresponding. So too are 4 and 8, 1 and 5, and 3 and 7. Next, let's look at alternate interior angles. Alternate means opposite sides of the transversal. Interior means inside the two lines. So 3 and 6 are alternate interior angles, so too are 4 and 5. Let's look at alternate exterior angles. Again, opposite sides of the transversal, but outside or exterior to the two lines. An example here would be 8 and 1, or 2 and 7. And then finally we can pair up angles by same side interior or same side exterior. Same side means the same side of the transversal. Interior means inside the two lines. So an example of same side interior would be 4 and 6, or 3 and 5. And then finally, same side exterior would be, for example, 2 and 8, or 1 and 7. And just like these words or these terms all apply to this picture over here, they also apply equally well to that picture over there. Some interesting things happen if the two lines through which you're drawing a transversal happen to be parallel. So I'm going to draw a picture of that. Here are the two lines. I'm going to try to make them look parallel. And then here's the transversal cutting between them, or cutting through them. And I'm going to tell my reader that these lines are parallel by putting these markings on them. And that way, even if they don't look parallel, my reader will know that they're supposed to be parallel. And one interesting thing that happens here once the lines are parallel is that if one of these angles, for example, say is 110 degrees, we know that its corresponding angle is also 110 degrees. And it's something that we're going to accept without proof. It's called a postulate. And Euclid, back in 300 BC, could not come up with a proof to show that these two angles will always be congruent to each other if these lines are parallel. And in fact, in the 1700s, there were some mathematicians who discovered new types of geometry that are based on these two angles not being congruent. But we're not going to concern ourselves with them this year, so we will just know that as long as two lines are parallel, corresponding angles are congruent. And from this information, we can actually fill in the rest of the angle measures. First of all, we know that vertical pairs of angles are congruent. So this angle down here is 110 degrees, and so is this angle down here. It's 110 degrees. We also know that a linear pair of angles add up to 180 degrees. So therefore, this angle here is 70, and its vertical pair is 70. And in similar fashion, this is 70 down here, and this angle is 70. And we are going to use these ideas a lot this year. If two lines are parallel, corresponding angles are congruent. And if two lines are parallel, then alternate interior angles are also congruent. And alternate exterior angles are also congruent. And finally, if two lines are parallel, same side interior angles are supplementary, and same side exterior angles are also supplementary. And we can call those theorems because they are things that we can prove as opposed to things we just have to accept as being true. Next, let's take a look at the converse of that earlier statement. If corresponding angles are congruent, then the lines are parallel. And this is also a true statement, and I'm going to draw a picture of this as well. Here are two lines. I'm not going to indicate that they're parallel because that's not in my hypothesis. Here's the transversal, But suppose that I know, for example, that this angle right here is 105 degrees, and that angle right there is 105 degrees. Then I can conclude that these two lines must be parallel. Because if corresponding angles are congruent, then the lines must be parallel. And in similar fashion, if alternate interior angles are congruent, then these lines must be parallel. Or if alternate exterior angles are congruent, then these lines must be parallel. And finally, if same side interior angles add up to 180 or are supplementary, then these lines are parallel. And if same side exterior angles add up to 180, then these lines must be parallel. So the converses of our earlier statements are also true. Great. Let's now solve a few problems. In this first picture, the 110 degree angle and the angle we're looking for are alternate exterior angles, and we know these lines are parallel, and if lines are parallel, alternate exterior angles are congruent. So that angle right there is 110 degrees. In the next problem, number 12, here again we have parallel lines, 84 degrees and the question marked angle are alternate interior, and alternate interior angles are congruent if lines are parallel. So that angle must be 84 degrees. In this next picture, number 13, these two angles are same side interior, and same side interior angles are supplementary. So that angle must be 80 degrees. And then finally in number 14, these two angles are alternate interior angles. So that angle right there must be 111 degrees. Let's now use this information to write a proof. And the proof I want to write today is one that shows that the three angles in a triangle always add up to 180 degrees. And to do that, I'm going to begin by drawing a diagram. I'm going to draw a picture of a triangle, and it's not going to have any special properties, it's just going to be a random triangle. And I'm going to label its angles 1, 2, and 3. And then across the top of that triangle, I'm going to draw a line through the vertex that's parallel to the bottom of the triangle. And I'm going to use those parallel symbols to note that those lines are supposed to be parallel, even though they don't look that way. And then finally, I'm going to make use of these two angles, so I'm going to label them angles 4 and 5. And what I'm going to try to prove now is that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. And when we write proofs this year, we will typically do two-column proofs. So I'm going to draw a big space. And in the first column, we're going to have our statements, which I'll call S. And in the second column, we'll have our reasons, which I'll call R. The first thing I'm going to note in my proof is that angles 4, 3, and 5 all add up to 180 degrees. And that's because together they form a straight angle. So I'm going to write that down. The measure of angle 4 plus the measure of angle 3 plus the measure of angle 5 adds up to 180 degrees. And I'm simply using angle addition there and the fact that a straight angle equals 180 degrees. Okay, next I want to make this observation. Angle 1 and angle 4 are alternate interior angles. They are inside these parallel lines and they are on alternate sides of this transversal. So the measure of angle 1 equals the measure of angle 4. And similarly, angle 2 is congruent to angle 5, so their measures are the same, because they are interior angles inside these parallel lines, and they are also on alternate sides of that transversal. So, the measure of angle 2 equals the measure of angle 5. And both of those, the reason for both of those is that parallel lines imply that alternate interior angles are congruent. And now finally, what we're going to do is say that since 4 and 1 are interchangeable and 2 and 5 are interchangeable, then angles 4, 3, and 5 adding to 180 degrees is the same as angles 1, 3, and 2 adding up to 180 degrees. So we're substituting here. We're going to write the original line again, but we're going to substitute 4 for 1, or I should say 1 for 4 and 2 for 5. So here we go. The measure of angle 1 plus the measure of angle 3 plus the measure of angle 2 equals 180 degrees. And here we were using substitution. And then finally, we have reached the point where what we have shown here is what we were asked to prove. So therefore we can write what many mathematicians do at the bottom of their proofs, QED. And it's an acronym, it's a Latin acronym, and it says Quod erat demonstratum. And it essentially translates to what has been asked to be proved has been proven. And that's it.